Hello Espers, welcome back to a new video. Today I'm going to be going through the Edexcel International A level Pure Mathematics 3 chapters on trigonometry. So all that you need to know for trigonometry in Pure 3. Now, there are some other information you might need to know. For example, the graphs, and you might be asked that related to the functions chapter, or you might need to use it for a certain calculus question with differentiation or integration, but I won't be going into those. Simply the questions that are specifically for trigonometry. Some of them you will be able to apply to the other chapters, but it's not like I'll be looking at those specific questions. Firstly, I'm going to explain chapter 3, the trigonometric functions chapter, and then I'm going to go through chapter 4, the trigonometric addition formulae, and after that we'll go through some exam questions together so that you have an overall idea on how to answer these types of questions, and I will be going through my thought process on how you should be able to answer the questions, what you should think about in order to figure out the right answer, because some of these questions can be puzzling. So, without further ado, let's start. The first chapter, chapter 3, trigonometric functions, looks into three new functions which we haven't seen before. These are the secant, cosecant, and cotangent functions. All they are the reciprocal functions of the original ones. What that means is that secant is simply 1 divided by cos, cosecant is 1 divided by sine, and cotangent is 1 divided by tan. That's all they are. Every value that you put in for cos, 1 divided by that, that's your value for secant, and so on and so forth. We know that we can write tan as sine divided by cos, so cotangent can also be written in terms of sine and cos, which would be cos divided by sine. In this chapter, you should be familiar with some of these graphs. Now, the sine graphs you have seen before, but let's see how we can use them to plot our cosecant graph. Because cosecant is just every value of sine doing 1 divided by that, the reciprocal value, we know that, for example, at this maximum point of sine, when it equals 1, 1 divided by 1 is going to be 1 as well. So the cosecant graph stays the same, just like we can see here for pi over 2 and pi over 2, sine and cosecant have the same value. When sine is minus 1, the same thing happens. 1 divided by minus 1 is also minus 1. So we get this repeated point in both of those graphs. We can see that the cosecant graph has a whole bunch of vertical asymptotes. Now, these asymptotes appear when sine equals 0. Because we know we can't divide by 0, if you're doing 1 divided by sine, and sine is equal to 0, you'll get an error. So here we can see why there are these asymptotes. If you familiarize yourself with the sine graph, and you are asked to plot the cosec graph, you will be able to recognize it because of the shape, and you can figure out some key information just like what I'm talking about here. For the functions chapter, though we won't be going into detail for that, there is some useful information to know. For example, that you can put in any values of x into your cosecant function, except of course the ones where sine x equals 0, because like we said, that's dividing by 0. And because sine x is always between 1 and minus 1, cosec x is always greater than 1 or less than minus 1. So I wrote this out as the absolute value of cosec of x is always greater than or equal to 1, because if we forget about negative signs, it's always going to be a number that is either 1 or bigger than 1, which we can also see here on the graphs, since it goes outwards, up, and down. A similar thing happens for our secant graph. When we draw our cos graph, when cos equals 1, secant will also equal 1, like we can see in these 2 points. When cos is minus 1, secant will also be minus 1, like we can see on these 2 points. When cos is 0, we can't divide by 0, so there is an asymptote for the secant graph. And just like before, we can put in any values of x except for the ones where cos x equals 0. And just like before, the cos graph is always between 1 and minus 1, so the secant graph is always 1 or greater and minus 1 or below. Lastly, we have the cot graphs. The tan graph, as we know, looks like this. So just like before, for any values where tan is 0, cotangent will have an asymptote. For example, at 0 and pi, we can see there's an asymptote for cot. But for values where tan has an asymptote, that is when cot equals 0. As our value of tan approaches pi over 2, the numbers shoot up and become really big, or they shoot down and become really, really small, which implies that you're doing 1 divided by a really big number. So a number, if you divide by a really big number, it approaches 0, just like you can see in your cot graph. So any asymptotes of tan are actually zeros on cot. So here we can see that cot x, just like before, we can input any values except when tan x equals 0. And that just like with the tan graph, it doesn't have any restrictions. It can go from to positive infinity to negative infinity. It doesn't, not like with the sec and cosec graphs, there's not that empty block in the middle. It gives out any possible value. These graphs don't appear as often in past paper questions, but it's useful to know them, especially with the functions chapter, where we still might be asked to describe the domain or range of a function, which is useful and the information I provided here. But it might also be needed to graph some of these functions or transform them. And we learned some of our basic transformations of shifting, enlarging, etc. in back in Pure 1 and Pure 2. And this can be revisited in Pure 3, so it's good to keep these fresh in your mind. And familiarizing yourself with some of these graphs might be helpful. The next part of the chapter requires you to know some new identities using the new functions that we found. Now, all of these can be derived from our original identity of cos squared plus sine squared is identical to 1, which is great. How can we get these identities? Well, what we can do is we can divide everything here by cos squared. If you divide cos squared by cos squared, it's just going to be 1. Sine squared divided by cos squared is tan squared. And then we're left with 1 divided by cos squared. Now we just learned that 1 divided by cos is sec. So 1 divided by cos squared is sec squared. And now we have a new identity linking tan and sec, which is useful when we're trying to answer questions later, which we'll take a look at. But what if instead we divided by sine squared? If we divide everything by sine squared, well, sine squared divided by sine squared will just be 1 again. Cos squared divided by sine squared, we just learned that cos divided by sine is cot. So cos squared divided by sine squared would be cot squared. And we learned that 1 divided by sine is cosec, so 1 divided by sine squared is going to be cosec squared. And that provides us with our second identity. 1 plus cot squared is identical to cosec squared. Neither of these formulas appear in the formula book, but if you've memorized sine squared plus cos squared equals 1, you can learn these as well, or you can simply divide by cos squared and divide by sine squared in case you don't remember them. So you can rediscover them in the exam if necessary. It only takes a few seconds. But if you prefer to memorize, and that's more for you, then go ahead. Now the last part of this chapter talks about how we undo trigonometric functions, which on our calculator was arccos or cos to the minus 1. So these are our inverse functions. We've seen these before, but now we're just taking a little bit of a look at their domain and range because this is related to some of the previous chapters, and it's also good to know their graphs. Now I'd like to start with the sine graph because the sine graph looks approximately like this normally. This is just a piece of it. Of course, it continues on like that. We know that all of our inverse functions are just reflections along the line y equals x, which we can see with my badly drawn diagram is approximately true. These functions are kind of flips of each other, mirrors, on the line y equals x. So if they ask you to draw this in the exam, you could use your original sine, cos, or tan graph and just reflect it along the line y equals x and see what it looks like. In this case, we can see that only a bit of the function is reflected. It doesn't continue onwards, down and up here. Why is that? Well, we learned in the previous chapters that we can't have a one-to-many function, or else that wouldn't work. So in this case, we're only taking a small snippet of our sine graph, and this is actually where those principal values that we learned about back in Pure 2 come back in. The graph always gives us the principal values which appear in this range of minus pi over 2 to pi over 2. And of course, you can take in any values from -1 to 1 because outputs any values between 1 and -1. Then a similar logic can be applied here, where we can see the inverse cos graph as well. It can take in values between -1 and 1, and in this case, it gives the principal values from 0 to pi. They chose to do a smaller upper chunk of the cos graph. For tan, because it can output any numbers from -infinity to infinity, since it goes up all the way, then that means that you can also put in any values for arctan, or tan to the -1. And then these will output values between -pi/2 and pi/2. I noticed that I put less than or equal to. That's not correct. It should be less than. Because, of course, we know that at pi/2, tan has an asymptote. So it approaches that value, but it never really reaches it. And that was a quick skim of the inverse functions, which aren't as important, but we still use them, of course, when solving questions. These are not unfamiliar topics. We've looked at these before, but now we're just looking a little bit at the graphs and also their domains and ranges, which can pop up in other topics as well. That is everything that covers the chapter 3, which is quite actually a short chapter. More of the important trigonometric things appear in the next chapter. The most important things that you might see from this chapter would be your identities of sec, cosec, and cot, and their new identities relating to our original 3 sine, cos, and tan. But before we continue, I would like to take a look at one more thing, which is quite useful and important to remember, which is the difference of two squares. I want to make sure that everyone remembers that if we have two numbers squared, for example, a squared minus b squared, then we can factorize this in this form. This factorized form could be useful, or sometimes it's useful to expand this form, because it can give you answers and help you manipulate trigonometric questions, and we'll see this later on. So just to make sure that everyone's on the same page, that we remember our difference of two squares, this good old trusty formula that we've had. Before we move on to the next chapter, I'd like to do 2 quick questions with you guys. If you're feeling confident with what you've just learned, you can try to answer these yourselves. So have a go first, pause the video, and then I'll answer this myself. Over here we have a question now. Instead of sine, cos, or tan, we have the sec function. Now, it's asking us to find the values of x between 0 and 2 pi, and we haven't learned about an inverse sec equation. So what we might want to do is rewrite this in terms of cos. Now we learned that sec is the same as 1 divided by cos, so we can rewrite this as 1 divided by cos of x plus pi/4, which equals 2. And we can get the cos onto the top by just flipping both sides of the equation. So we get cos x plus pi/4 is equal to 1 divided by 2. Because we flipped the left-hand side, we also flipped the right-hand side. Once you get familiar with these questions, you'll notice that if you're left with this simplified form of an equation to solve, all you can do is you can replace it with its counterpart, sine, cos, or tan, in this case cos, simply by flipping the opposite side in a sense. So maybe that's a quick trick in order to answer these questions quickly. And because we're more familiar with cos, we don't even need to worry about these new functions that we found so much. We can always rewrite them at some point in our old traditional friendly functions. So in this case now, I can solve for x just like I would in any question back in P1 or P2. So using our good old-fashioned method of solving a cos equation, and looking for how many solutions there are in this range by drawing our little graph. You can see my bad quality cos graph over here. We find that x equals pi by over 12 or 17 pi divided by 12. Now the second question I would like to do is an actual question that pops up quite often, is where they might give you some equation and ask you to prove that it's identical to another equation. In this case, I've picked out this question over here. Sorry for the bad quality. But we can see that we're using our cosec and our sec, which are new equations. So let's practice rewriting these identities. We have seen questions like these back in P2, but those only involved sine, cos, and tan. So let's try to solve this using our new identities that we know and simplifying it into this form. Now the first thing that goes through my head is that having these two separate fractions is quite tricky, so I would combine these fractions. And to do that, I need to get a common denominator. If we get the same common denominator, as we can see here, we end up with this at the numerator and this on the denominator. The easiest way to get a common denominator in this case would be multiplying them together. But what do we notice? Well, this denominator resembles the equation that I was talking about before, which was the difference of two squares. When we have something in the form of a minus b and a plus b, that's the same as a squared minus b squared, the difference of two squares. So let's simplify the top and expand the bottom that way. The cosec plus cosec becomes 2 cosec. And then the 1 minus 1 cancel out, so we're just left with 2 cosec theta on the top. And in the denominator, we are left with cosec squared minus 1 squared, which is just 1. So we have this. Now we can see that we want to end up with a tan and a sec in our equation. So what we need to look at is if there are any identities that we know. We've got a cosec squared here, which whenever we see squares, that should immediately make us think that, oh, we have a whole bunch of identities related to squares. So let's write out what's the new one we just found for cosec. And that is cosec squared is 1 plus cot squared. But we can move the 1 over to get cosec squared minus 1 is identical to cot squared. And this is the exact same form as what we've got down here, so we can replace this with cot squared. Now, because 1 divided by tan is cot, the same thing is true that 1 divided by cot is tan. Because cot is 1 divided by tan, it means that tan is also 1 divided by cot. So we can rewrite this as 2 cosec theta tan squared theta. We can see we're getting closer to our answer. We have the 2 over here and we have a tan, but we have tan squared and we have a cosec, but we need a sec and we only need 1 tan. So what I would do is I'd separate this tan squared into tan times tan. Why am I doing this? Well, I'm trying to basically keep this one by itself and alone so that I can go back to it later when I'll need it. So instead, let's work with this tan over here. We know that tan is sine divided by cos, so let's rewrite it that way. And what we'll notice is that we have sine times cosec. Remember, cosec is 1 divided by sine. So what we're basically saying here is sine divided by sine, which means these two are going to cancel each other out, and we're left with 1 divided by cosec. But we've learned that 1 divided by cos is sec. So we can write this as our final answer of 2 sec theta tan theta, which is the same as what we started with. This did take a little while, and you might be surprised that I did some things, and like, why did you choose to do that? Why did you go down this specific route? Why did you split the tans and then decide, oh, let's do sine divided by cos? Why didn't you turn it into cot again? Well, the truth is, I didn't know what I had to do. What I noticed is that at first, for example, I could combine the fractions, and then I found out, oh, look, that's the same as cot squared, so I can replace this with the cot squared. Then I know that I had one tan ready, so I said, let's try something, and let's try to leave one tan alone and just work with what we have left. Maybe we can somehow rewrite this part to be the remaining part that we were missing. And we could. And I knew we could do this because I tried sine divided by cos. I actually wasn't certain if that was going to be in the right direction. These questions always fall into place when you're working through them. So if you rewrite tan as sine divided by cos, you might just happen to come across the answer, and that will always be the case. There's always many different ways to also answer these questions, especially the ones in exams. There might be different methods to do it. If you look through exam papers, the mark schemes will always have way 1, way 2, way 3, way 4, so on and so forth. So you might come up with a different way to answering certain questions, which is okay, because all roads lead to the answer. Now this is the end of the first part, where we've looked at chapter 3, trigonometric functions. We have learned what sec, cosec, and cot are. We've learned what their graphs look like. We've revisited what our inverse function graphs look like, sine to the -1, cos to the -1, and tan to the -1. And we've learned some new identities along the way, and also quickly revised the difference of two squares. So this should give you an overall good basis for chapter 3. So let's move on to chapter 4. Chapter 4 provides us with 3 new identities. These are called the addition formulae. Now, the addition formulae are basically if you have two separate numbers and you wish to add them together in a sine, a cos, or a tan function, or you can even subtract them, then you can rewrite this as separate sines, causes, and tans with just that one number each time. This can be very useful when manipulating algebraic expressions, and we'll look through a small example now. I want to point out that this plus or minus means that you can either use a plus here or you can use a minus. For example, if I want to use a plus here, then I'm also going to use a plus here. But in the cos graph, because you can see this one is plus or minus, and over here we've got a minus plus, that means they have to be opposite signs. If I wanted to add these two together, I'd have to subtract what's on the right-hand side. You will all be very happy to know that these are provided in the formula book, all 3 of these, so you don't have to memorize them. You can just look into the formula book and use them at your leisure. But I 100% recommend doing practice questions with these, because even if you don't have to memorize them, you should be able to recognize them and know when to use them. Especially certain formulas that we're going to look at a bit later, called the double angle formulas. Just a very simple example to practice using this new tool that we've learned. What is the exact value of sine of 75? Now, we don't know what that is, but we do know that 75 is the same as 45 plus 30. And both of these are common angles that we know. We know what sine of 45, cos of 45, sine of 30, cos of 30 are. So using the new formula we just learned for sine, if we have one number plus another number, so for example 45 plus 30, we can rewrite this as sine of 45 cos of 30 plus cos of 45 sine 30. And because all of these are common angles that we know the values of without a calculator, sine 45, cos 45, sine 30, and cos 30, we can calculate an exact value for sine of 75. Sine of 75 is root 6 plus root 2 divided by 4, which is pretty cool. Something that ends up being used a little bit more are the double angle formulae, which you also learn. These are not given in the formula book, but they're very easy to derive from the addition formula, so you can just figure them out using these formulas, or you can memorize them as well if you prefer. Through a lot of practice, it's likely you will have them memorized. The double angle formulae are basically what if x equals a, which also equals b. So what if these two angles are the same? And what we're going to do is we're going to add them together. If we start with sine, we get sine of x plus x, which is, we have x plus x, which is the same as 2x. And on this side, we've got sine x times cos x and cos x times sine x, which is the same thing. We can put these together to get 2 sine x cos x. So this is what we call our double angle formula, where if we have a double angle like 2x, you can split this into one angle, x and x's, just separate x's. This can be useful if you had an equation of, for example, sine x plus sine 2x equals 0. You can now solve this equation because before it was tricky since these two had separate amounts of x inside. We couldn't combine these in any way, but now we can rewrite this into regular just x's inside of the function, so we can solve this equation much easier. If you would like to have a go at replacing a and b in the other two addition formulae with x and try to get the other two double angle formulae for cos and tan. I'm going to do it as well now, but I'm going to do it quickly so you can pause and do it yourself or follow along with me. Because we have two causes being multiplied together, this is going to be cos squared x, and these two sines multiplied together are going to be sine squared x. So we're going to be left with cos 2x is identical to cos squared minus sine squared x. The two tan x's on the top will combine to make 2 tan x, and on the bottom we have 1 minus tan squared x. And so we've used our addition formulae to come up with our double angle formulae. The last thing I want to note is that specifically for the cos one, there are actually different ways of writing it. You can use our identity of sine squared plus cos squared equals 1 to rewrite this. So what I recommend, if you want, as an exercise, you guys can try to replace the sine squared with 1 minus cos squared and this cos squared with 1 minus sine squared, and see what happens when you do that. I'm going to just write out the solutions, but you might want to work through them yourselves. So this is another way that you can write out the cos 2x formulae, and it might be useful to be able to recognize these in case they appear somewhere and you have to rewrite it in the form of a double angle. Now there's one last bit for trigonometry in Pure 3, but I believe that this is easiest explained with an example. So I'm going to now start with the exam questions, but this specific bit first is also going to be explaining the last part of Pure 3. This is the last question of January of 2020. We will be focusing on Part A. Part B and C are more related to Chapter 2, which is the functions chapter. Now, you can still go through it and try it out yourself, but we're just going to be looking at Part A. The idea of the final part of the chapter is that whenever we have a cos and a sine together in some form, we can rewrite this as a single cos or a single sine, just like we have here, but we're going to have some number that we're multiplying by and possibly some extra number inside that we're adding by. Let's see how we can do this. Now they give us quite a hint telling us that it can be written in the form r cos theta plus alpha. So we can say that this equation that they've given us has to equal r cos theta plus alpha. And all we have to do is find out what the value is for r and for alpha. The trick to solving this kind of question is first we're going to be splitting this into cos thetas and cos alphas using our addition formula that we just learned. So in this case, A is theta and B is alpha, so we can split this by doing. I've put the r in front because the whole thing, of course, is going to be multiplied by r. Now I've rewritten the order that we have everything in, just so it's a little clearer for what I'm going to do next. What we can see here is we have something cos theta minus something sine theta. And our original equation is something cos theta minus something sine theta. So what this is hinting at is because we've got a cos theta here and the only other cos theta is here, the number in the front has to be the same as the number we have in the front here. In other words, 5 has to equal r cos alpha. Because we know alpha is just a number, cos alpha is also going to be some number multiplied by r gives you 5. We have a minus something sine theta 2 here. This has to also be the same as what's on this side here. So 4 equals r sine alpha. And what we're left with here are two equations with two unknowns. All this is a pair of simultaneous equations. And we can solve this using some nice methods. And the reason I did this is because these r's are just going to cancel each other out. And we're left with sine alpha divided by cos alpha, which is the same as tan alpha. So tan alpha is equal to 4 over 5. And we can find our value of alpha in radians is going to be 0.675. How many decimal places do they want it to? To 3 decimal places. So 0.675 radians. In the question, they're asking us for the exact value of r. So plugging it directly back into the equation isn't going to help us. What we have to do instead is we're going to, again, combine these two equations in a certain way. And what we do this time is instead of dividing the two equations together, we're going to square them and add them together. Five squared plus 4 squared is just 41. And this is r squared cos squared alpha plus r squared sine squared alpha. And we can factor out the r squared to get cos squared plus sine squared. Well, what do we know about sine squared plus cos squared? Well, that's just 1. So this whole term is equal to 1. So we're just left with an equation in terms of r, where r squared equals 41. So r equals plus or minus root 41. But they told us in the question that r is greater than 0, so it has to be positive. So that means that r is equal to the square root of 41. This method involves us using our addition formula to re-expand out these brackets and then find these two equations in terms of r and alpha, and then use them in order to find out what the value of alpha is and what the value of r is. What you always end up doing is doing one divided by the other and then squaring them and adding them together. These are the two ways that you're going to combine the equations in order to get your value of r and your value of alpha. Some of you might prefer to memorize equations, or with enough practice you'll notice that r is always going to be the square root of this number squared plus this number squared. It's always square both numbers, add them together, square root them, that's your value of r. And once you have that, you can use one of these equations to get your value of alpha because you don't need it to be accurate. Alpha is going to be an approximation. These questions can also be asked with the sine addition instead of the cos. So instead of having a cos here, they might ask you to do it in a sine form, but then you end up following the same basic steps. You can find the R value the same. And speaking of exam questions, let's end this one off by trying out an exam question from January 2021. This is past paper if anyone wants to check it out. Let's try to solve it together. If you're feeling quite confident, please go ahead and try to solve it yourself first. And if you get stuck at any point, you can go and watch what I do and then continue trying to do it yourself. All right, so we can see here that I've got a equation in terms of sines and causes, and I want to show that this is equal to cosec x. Basically, always whenever you see a trigonometric identity question, it's usually easier to start from the complicated side and simplify your way to the side which looks less complicated, because it's much easier to simplify something than make it into a big complicated mess. What I can see here is that I've got double angles, and I know that my final answer doesn't have any double angles. So what I might consider is using my double angle formulae to rewrite these in terms of regular sine x and cos x. I find it helpful to quote my formulas on the side whilst I'm doing my calculation and proofs. That way it keeps me on track of what have I done, how did I get to a certain value. Now we know that we have three different forms of cos 2x. Which one should I use? Well, I can always rewrite them into any other form if I need to, but just by intuition, knowing that I have a denominator of sine x, I'm going to use the one which is only with sine x and see if that helps me. So now that I've written down my formulae, I can apply them into my equation. In the first fraction here, we can see that we have a cos on the numerator and a cos on the denominator, so I can cancel them out. And over here, 1 divided by sine x is cosec x, and minus 2 sine squared x. One of those signs are going to cancel from the top, so I'm left with minus 2 sine x. And we have 2 sine x minus 2 sine x, they're going to cancel out, so I'm left with cosec x. And so we've answered part A of the question, so we can move on and try to answer part B. It says, hence solve for theta in this equation. Now, because it's saying hence, it means we have to use the previous part of the question to answer this, and we can see that this is practically the exact same as what we have over here, but the angles are all doubled in this one, so x is going to be equal to 2 theta. So if I write out thanks to the previous part of the question, we know that this whole thing over here is going to be cosec 2 theta. And because we've got cosec on this left-hand side and we have a squared on the other side, I'm thinking let's use our identity for cosec and cot to rewrite this in terms of cosec. Also, because both sides have 2 theta in their equation, I don't see any need to use my double angle formulas to write this in terms of just theta, because just like we did back in P2, we know how to solve an equation. We will just have to change our domain for theta later, which we'll see in a bit. Rewriting all of this and moving it all to the same side will give us, let's see if this is a nice polynomial which factorizes. Oh, apologies. It's minus 10. Now that we factorize this, that means that just like with our sines, causes, and tans back in P2, we can say that cosec 2 theta equals 2 and cosec 2 theta equals minus 5 over 3. Those are our two solutions to the quadratic equation. You can type this in your calculator to check. Now, just like I've said before, we don't have any inverse function for cosec, so we can rewrite this as sine instead by basically flipping what's on the other side. So sine 2 theta is 1/2, and sine 2 theta is minus 3 over 5. Both of these are between 1 and minus 1, so that means that it's in our range of possible solutions, so we can accept them. We don't have to ignore any values because all of these are possible answers so far. Now, our range is minus pi over 2 to pi over 2. If we extend our range for 2 theta, then it's from minus pi to pi, which is going to be our sine graph. This will be a half, minus 3 over 5 is somewhere here. We're going to have two solutions for each one. So that means that all of our solutions for 2 theta are minus 2.498 minus 0.644 pi over 6 and 5 pi over 6. And then if we divide them all by 2 to get our values of theta, how much accuracy do they ask for? 3 significant figures. We get these 4 solutions for theta. Many P3 questions, specifically trigonometric only questions, go in this format where they will give you some sort of identity they might ask you to prove. This is a very common type of question. And then they might ask you to use your new identity that you found in order to answer a complicated equation by simplifying it, which is what we did. The other type of questions they can ask is the one that we looked at before with the with combining this cos and the sine into one cos or one sine. This is an example of a question, if you want to try it out yourself, where they used sine and cos, where you have to use the double angle formulas to rewrite them. So to recap, what we've done in the second chapter is we've looked at the addition formulae, the double angle formulae, and how we can rewrite a sine and a cos into a single term. That is the basis and the most important part of the trigonometry section in Pure 3, I'd say. Those are what appear the most, including the identities in Chapter 3. I hope you found this video helpful and that we went through a few exam questions, and I hope that they made sense as well. If you have any questions or any specific questions you would like to see me go through as well, feel free to comment or send them to me, and I'll be happy to take a look at them. If you have any other questions, feel free to contact me, and have a nice day. Thank you so much. Bye.